Hello guys, today I am going to talk about the Orion, okay, the re-entry vehicle. This is the re-entry vehicle which have a lot of pressure in the nose while entering to the atmosphere, okay, like this. I did all the ANSYS simulation for different stages. So today I will talk about this project, okay. Let's go from the starts. It is specifically done at 20 km altitude, okay. Let's talk about re-entry vehicle. What is it? This is designed for human exploration. It is carry crew to the space and it sustain crew during the space travel, provide emergency launch, and provide safe re-entry from the deep space. It is blunt body designed to withstand the critical load condition. During re-entry, crew medal undergoes the high speed entrance. This re-entry carries the high thermal load and aerodynamics. So we are going to study that aerodynamics while returning to the earth from the space. So what is the problem with the re-entry vehicle? A re-entry vehicle comes with the high speed and high pressure from atmosphere. Okay, so it forms the detached shock. We are going to see in the ANSYS results. So shock results in rapid pressure and temperature rise at the blunt body, and so blunt body need to manage all this stress and still come to the earth and have the safe landing. Okay, and vehicle geometry and Mach number play the vital role handling this as condition. So we are going to discuss that. What is the aim of the project? To analyze how Mach number affect detached formation, stagnation, pressure, shock stand-up distance. Okay, and these are the literature from where I got the many ideas and help me to complete this project. Okay, this was the Mach number and shock stand-up distance. These are different for the different Mach number, different speeds like this in subsonic speed, supersonic speed. We can see in the figure how far boson is formed. Okay, as you can see in second figure, its distance is too much, but as you can go into supersonic, the distance is low. That means we have a high pressure, high condition. These are the governing parameters that need to be studied. So this is the geometry I use. So you can get your geometry from this paper. Okay, yeah, this is geometry. You can get it from this paper, or you can have geometry from this paper. Okay, and for the meshing I use 2D planar model and refine the shock capture region and nose region, and did the global meshing with the body of influence, which is so easy. Guys, don't forget body of influence, it's so easy. And I use density based solver, energy, turbulence. Okay, and I also use the Sutherland air viscosity. Okay, that's important. And for the atmosphere, as I say that for different altitude the pressure and temperature is different. Okay, so I especially did it for 20 km height from the ground, which has only 5000 Pascal, and I set inlet outlet every side to the pressure field. And for the meshing validation, I did it for Mach 2 and I reduced different sides as you can see, and I got around the same stagnation pressure and shock distance. Okay, now let's talk about the different shocks in Mach number. As you can see in Mach number 0.5, we don't see any shock waves. The pressure is gradually increasing and velocity is slowly decreasing towards the notch, so we don't see any shock. But as we move forward to Mach number, we kind of see little bit shock waves. Okay, you are seeing this curve where little bit shock wave, but if you move to the Mach number 2, you will get good shock wave. Okay, as you can see the graph, the pressure is increasing very short time, increasing steadily. Okay, there is no gradual increase, it's just the okay immediate increasement. And if you move to the higher Mach number, our shock standoff distance is decreasing and shock will become more and more strong. Okay, also for the axisymmetric model, I model the all axisymmetric and tried for Mach number 2, the shock of distances decreases, and but the pressure is almost the same. To talk about N, I got to know that planar and axisymmetric results are totally different, eh, and axisymmetric results are closer to real one. But planar results is good for showing the trend and do the analysis. And we are moving forward towards the analytical modeling. This is the different models that I did. Excel models I calculated for the different beta angle. Okay, I calculate pressure ratio, temperature ratio, and from that result I got to know that it's we move forward the higher Mach number, our beta angle is decreasing. That means higher, stronger shock. Okay, so we got the around same trend analysis from the CFD and now this analytical method. Also, if we compare it to the literature, influence of Mach number is really very high in aerodynamics behavior, and we found that detached shock is established in Mach 2 and above, but we don't get any shock waves in Mach 1 and lower. So the final results, we can say that the whole experiment is done in 12-kilometer altitude, and we did it for different Mach number from 0.8 to 8 Mach number, and we got to know that if we increase the Mach number, the pressure ratio and the shock strength is increased. So we have to, while designing the any re-entry vehicle, we have to study about the Mach number and their geometry. In different velocity, we have to make the geometry withstand their pressure and velocity. Okay, then thank you.